Hello everyone. In this video I would like to show you how to create a model that represents the hydraulic performance of a bioretention system. The example that I'm gonna create the model for is presented in this paper by Ali Khani et al. 2020 that is published in the Journal of Sustainable Water in the Built Environment. So if you want to get basically go into the details or look at the details of the model, you can look at this paper. But then in the paper, actually what we did was that we simulated a model of basically a dual bioretention system. So the effluent from one bioretention cell goes to another bioretention cell. In this example, to keep things simple, I'm just going to model one of the bioretention cells. So the diagram that you see is basically shows how the system is configured and all the parameters that we're going to use. So we have surface ponding, of course. We have some engineered soil with high permeability. The soil properties are given in this box, and then we have this aggregate storage layer. We're going to model the infiltration water into the soil until it gets to the groundwater. And then we have this internal storage system. So what that means is that there is the under drain pipe is placed at the top of the aggregate storage layer, and then we have this riser pipe that basically what it does is that it keeps the water, actually holds the water in the system. We have this overflow. So this is our overflow that we're going to model as a weir. And then we have this manhole, and the effluent goes into the sewer network. So the elevations are of all the layers are given. We want to model the pond using a sort of a rating curve that basically expresses the storage, the water stored in the pond as a function of the water depth in the pond, and then that's pretty much it. So we have this inflow. I'm gonna use the data that I have to represent the inflow, and then we're gonna do the simulation over a period of a year. So just one more point. In this example, I'm not gonna consider evapotranspiration. But you can easily include evapotranspiration from the engineered soil or from the pond using some other instructional videos that I've posted on YouTube. So basically I'm going to keep this diagram in the background so that since I'm going to need to go back and forth to look at some of the data and values that I'm going to need while I'm creating the model. So let me go to OpenHydroQual. So here is my OpenHydroQual window. I'm going to move this away. Let me expand my window a little bit so that you can see everything that is going on. So I'm going to start from basically creating the pond. So in order to add the pond to my model, I need to add this pond plugin. So I'm going to go to preferences. By the way, there are some other components in the pond plugin that we're going to use. So I'm going to go to preferences, add plugin, and then I'm going to pick the pond. Pond is actually the top one. So I'm going to add the pond plugin, and what that does is that it gives me a few components. One is the aggregate layer, which we're going to use later on. We have the stormwater pond, which I'm going to use to represent the surface ponding here, and then there are some connectors. Some we get a weir here, we get a white channel, which we're not going to use in this case, and then we have some connectors. We have a drain pipe. We have connector from aggregate layer to soil, and then from soil to aggregate layer, which these are the things that we're going to use later on. But at this time, what I'm going to do is that I'll just add the stormwater pond. And by the way, what I'm going to do is that even though I'm going to keep running the model, even though it's not before it's complete, I'm going to run it, and that's a good practice to see if what we're doing actually makes sense. OpenHydroQual is very much what you see is what you get. So basically, the system that we see is what it should be kind of modeled. So So even if you don't have any outflow from the pond, or if you don't have any soil underneath the pond and so on, if we run the model, we're going to still see some results, even though the results may not be kind of physically realistic. So anyways, that gives us some clues about whether what we're doing is actually what we expect to be done. So anyways, we have the pond. So let me just so basically now let me assign the properties of the pond. So I'm going to click on the pond, and then what I'm going to do is, you know what, actually I'm going to expand this property box so that we can see all the property names. So initial storage, I'm going to keep it at 0. Now if I go back to my drawing, what I have is basically I have this rating curve which expresses the storage in the pipe in the pond as a function of the depth. So basically here, this coefficient, which is 8,864, is our essentially alpha coefficient. Our beta coefficient is 2. So if you see here, it says this is the beta exponent in the rating curve that is expressed as S is equal to alpha d to the power beta. So, and then the beta by default is 2, so I'm not going to change that. I will have to add my inflow time series to the pond. So what I'm going to do is that I'll click here to the inflow, and then I have this inflow file that is saved, and then I'm going to put it on a website, and I'll provide the link in the comment section of the YouTube video. But my inflow file is actually this one. So this is St. Francis Upper Inflow.csv, which I'm going to pick. I can look at how it looks like. So this is my inflow. So it's actually the inflow is essentially I have values over a period of a year from September. So I can say from end of September or 1st of October to the October next year, right? So, and that's going to be my simulation period. So now I'll adjust my simulation period later on. Let me also assign the alpha coefficient, which is 8,864. So this is going to be 8,864. And the units are all SI. So when you use rating curves, the units are all I can't say SI basically because the day units are basically the time units are in days. So let me save this as a save this file as bioretention. But anyway, so but in the rating curve, the units are all in SI. So then what I can do is that actually I can run the model right away. Okay, so let's see what happens if I run the model. So what I need to do is I have to go to my settings, general settings, and then I'm going to change the start and end time to represent my data. So this is going to be the end time is going to be September, actually I can say October 1st, so 10/1/2015, and then it just automatically changes it to September 30th. But and then the start time is going to be again September 1st. Oh, I'm sorry, September 1st, 2014, right? So then okay, so I can run the model right now. So what I will have is basically I have an inflow going to a pond, and then nothing will happen to that inflow. So basically water keeps basically the amount of water keeps increasing in my pond, and the water level will go up and so forth. So let's do that. So I'm going to just go to this the top toolbar, and then I'm going to click on run. So it's quite fast because nothing interesting is happening, and this is done. Our 1-year simulation is done. Now we can look at several things. So I can right click on the pond, go to results. I can look at the storage. So this is my storage. As you can see, it keeps going up. They had this big event that contributed into most of the runoff throughout the year. Uh, but then the storage actually keeps increasing. We can also look at some other things like, I don't know, water depth, for example. So this is the water depth, which goes up to around, I don't know, 1 meter. And then I can look at the hydraulic head, and then the other things we don't have. We can look at the surface area of the pond too. So the surface area is also calculated. As you can see, surface area goes to something kind of unreasonably large, but we know that this is not realistic. So next, what I'm gonna do is that I will add the soil underneath the pond. So in order to do that, what I have to do. So this is going to be the engineered soil. In order to do that, what I will do is that I need to add a plugin called basically unsaturated soil. So I go to plugins, and then I pick unsaturated soil. So this is unsaturated soil. It's as variably saturated. Of course, it can be saturated too. As in this model, it'll be saturated during some stretches of time. So I'm going to pick this one, and so the soil plugin is now added. So I get some new components. I get a soil variable saturated soil block right there, and then I have some connector. I can have horizontal soil to soil connector. I have vertical soil to soil connector. I have surface water to soil connector, which is the one that I will use, and so on. So let me add this soil block too. So I'm going to add a soil block, and I'm going to basically move it here underneath my pond, and let's assign the parameters for the soil, by the way. So basically the bottom elevation. Oh, by the way, I forgot something. I need to also assign the bottom elevation of my pond. So this is the bottom elevation of the pond, which is 0 right now. But I know that since my coordinate system is based on the sea level, it's actually the bottom elevation of my soil is 158 meters. So let me correct that one. So the bottom elevation of the soil is going to be 158 meters. The bottom elevation of the soil is going to be 157.37. So it's basically, this soil layer is something around 63 centimeters. Okay, so let's do that. So basically this is going to be 157.37, if I'm not mistaken. Let's make sure. 0.37, that's correct. And then the depth of the soil layer is going to be 0.63. So for the depth of the soil block, I'm going to assign 0.63. And then the other properties that we need to change is, I'm going to keep since this is a very highly permeable soil, the Wangen-Eckton parameters and so on are not going to really matter that much, but they're actually the same. The default values are the same as what they're supposed to be. So what I know is that the hydraulic conductivity has to be 10 meters per day. Then the saturated moisture content is 0.4. The residual moisture content is 0.05. They are what I mentioned in my diagram, and the only thing I have to make sure to do is the initial moisture content cannot be 0 because my residual moisture content is 0.05. So this is going to cause some problems. So I'm gonna change this to, let's say, a 0.2. So initially when we run the model, the moisture content at the beginning of the simulation is going to be 0.2. Okay, so one more thing that we need to do is that we need to assign the base area of this engineered soil. So the area of the basin area is that we're going to consider for the bioretention system is 354.52. That's the area that we, of course, the area of the pond is going to change depending on how much water is in it. But as an average, basically what we're going to do is that we're going to just assign the area of the, maybe the area that is considered for the design and so on as our basin area, which is 354.52. So let me also assign that to the soil. So basically what we have is that we have this bottom area of the soil block. So this is going to be 354.52, 354.52 square meters. Okay, so now we have the area set. Now next, what we want to do is that we want to connect our pond to the soil so that infiltration can happen. So in order to do that, I'm going to use this connector, which is called surface water to soil connector. So I'm going to pick that one, and then I'm going to connect. So now this connector, it doesn't basically it doesn't have any properties. It only has a name, which we can change, of course. But I'm just going to keep it what it is. So then, okay, next step, we're going to add our aggregate layer. So let's do that. So in order to add aggregate layer, we're going to use this this icon, which is called aggregate zone. So I'm going to click on that one, and then we're going to have an aggregate layer added to our model. So now let's see what properties we're going to assign to the aggregate layer. So essentially, all we need for the aggregate layer, of course we need the porosity, but I'm going to keep it at 0.4 in this case. And we have a bottom elevation which is 157, and then the top elevation of our aggregate layer, which is the bottom elevation of our engineered soil, is going to be 157.37, which means that the depth of the aggregate layer is going to be 0.37 meters. So basically this is going to be bottom elevation is going to be 157, and then I mean basically actually this doesn't need a depth. So the aggregate storage layer does not need a depth, so I don't need to enter the depth. I need to enter the base area, which is going to be my 157.37. I'm going to copy that from here, and I'm going to enter that right there. And other than that, I don't need any other property. We can assign some initial water depth. So that's going to be the water that prior to our simulation is stored in the aggregate layer, but I'm going to keep it at 0 for the time being. Then so that's what we have. And then next thing, we have to connect our soil to the aggregate layer so that we allow infiltration from the engineered soil to happen to the aggregate storage layer. So what I'm gonna do is that I just pick the use the soil to aggregate layer link. Now here, if you look at the icon, the soil is above the aggregate layer. That means this connector is used when our soil is above the aggregate layer. So I'm gonna connect, and then for the link, of course, again, we don't have any properties other than the name, which I'm not gonna change. So this is what we have. Now, to make sure that we've done things correctly up to this point, I'm gonna run the model again and then see if things are gonna happen according to what I expect. And what I expect is, things are going to be pretty similar to the previous case, with the exception that some of the inflow initially is going to infiltrate into the soil and then go to the aggregate layer, but the aggregate layer and the soil will fill up, will get saturated very quickly, and then no infiltration happens afterward, and water will start building up on in our pond. So let's just run this. It's going to take a little longer. Okay, simulation is done. Now let's look at several things. For example, we can look at the hydraulic head in our aggregate layer. So I can look at hydraulic head here, and as you can see, it starts from 157, it starts building up, and then it keeps on rising because the water is actually filling up in our soil. We can look at our infiltration rate. So I can look at, for example, right click on this link connecting the pond to the engineered soil, and then look at the flow. And initially we have a little bit of flow, but then our aggregate layer and soil will fill up really quickly, and then we have a little bit of infiltration later on because of just the pressure head that is building up in the pond. So now is the time to add our native soil. So to add the native soil, I'm going to use this array feature. So basically what I'm going to do is that I will discretize the native soil is 4 meters deep. So basically the top elevation of our native soil is 157 meters. The bottom elevation is 153 meters. And what I'm going to do is that I'll discretize this 4 meters into 4 layers, each of them with a depth of 1 meter. Now keep in mind that you can discretize it any way you want. You can discretize it using finer grid or a kind of a rougher one. Of course, the finer one it gets, the infiltration is going to be modeled more accurately, but then the computational costs will go up. And then but for this particular case, we may not really care as much about the how accurately we are modeling infiltration, percolation into the soil or recharging the groundwater. So I'm going to actually use 4 grids. So let's do that. So what I'm going to do is that I choose this menu called Add Objects, and then I use Create Array. So I'm going to click on Create Array, and it gives me this dialog box. And here what I want to do is that my blocks are variably saturated soil blocks. So that's how I want to model my native soil. And then my connectors, these are the connectors that will automatically connect each variable saturated soil block to each other. So that's going to be basically vertical soil to soil connectors. Actually you can use this tool to create 2-dimensional grids, but in this case we only want to create a 1-dimensional grid. So the number of grid cells in horizontal direction is 1. The number in vertical direction is going to be 4. Okay. Then I can click on Next. So here I need to provide the properties. So basically let's start from the saturated moisture content. So the saturated moisture content, this is the value. So the saturated moisture content is 0.4. The residual moisture content is 0.095. So that's something that I need to change. So the residual moisture content is 0.095. I'm going to keep the specific storage what it is. I'm going to keep X valued what it is. We don't have evapotranspiration in this case. The initial moisture content, I'm going to assign a number that is between my residual moisture content and the saturated moisture content. The saturated hydraulic conductivity is 0.0624 meters per day. So it's basically going to be 0.0624 meters per day. The Wangenecton N parameter is 1.31. So this is what I'm going to do, 1.31. And by the way, this X and Y, they're just where the blocks are going to be shown on your GUI screen. So they basically only have a graphical purpose. But sometimes it's we can use them to place the array where we want to place them, so that we don't need to drag them later on to the place we want them to be. The Wangenecton alpha parameter is given to be 1.9 per meter. So let's do that one. So we're going to do 1.9 per meter. Then now in terms of, so what I'm going to do is that if I move my cursor here, you see that coordinate is shown right there. So basically the Y is around, if I want to place my blocks here or start placing the blocks around here, it's going to be around 1200. If I keep the 900, the blocks will be created up there, and then I have to drag them down. So it's really not a very important issue, but I'm gonna assign 1200 for Y. The area, the bottom area of the soil block is, of course, it's going to be the bottom area of my basin, which is 354.52. So I'm going to say 354. I'm sorry, 354.52. The depth of the soil block is going to be 1 meter. Then the bottom elevation, so this is the thing. What we'll do here is that we provide the bottom elevation of the top block, and then we provide an increment, a vertical increment. So as the cells are going down, or actually we go in vertical direction, how we want the bottom elevation to change. So this is actually an increment. So basically the bottom elevation of the top soil block is going to be this 157 minus 1, which is 156. So this is going to be 156, and then the increment is going to be minus 1. So what that means is that as the increments proceed, decrease the bottom elevation by 1 meter. And that's pretty much it. I can change the name too. Let's call it native soil. I think I have assigned all of the parameters that are needed. You can always change the parameters later on after things are created. So now I'm going to go to next, and basically for the link properties, we don't have any properties, so it's just a name that we can change, and I'm going to keep the name what it is. So I'm going to click on generate, and now we have our native soil blocks added to our model. Okay, we just readjust them a little bit. So so we can inspect the properties. For example, I can pick the top one, and you'll see that the bottom elevation of this one is 156 meters. The bottom elevation next one is going to be 155, and then 154, and so forth, right? So the next thing is basically what I want to do is that I want to connect my aggregate storage layer to my native soil. So now basically for that purpose I use this link, that is aggregate layer to soil link, and as you see, the aggregate layer is placed above the soil, so that means this is the one we need in this case. So I'm going to click on that one, and then I'm going to connect my aggregate storage layer to my top soil layer. And again, for this link I have no properties that I need to assign. Of course I can change the name, but I will not do that in this case. And that's it. So basically one thing is left, and that is to impose our basically bottom boundary condition. So the bottom boundary condition, what I'm going to do, I can actually place a groundwater, but the problem is if I place a groundwater, the groundwater can fill up, the pressure can build up as water basically enters the groundwater block, unless its capacity is sort of infinity. So instead of having an infinitely large groundwater block, what I will do is that I will use a fixed head boundary. And basically the fixed head boundary doesn't have to be the groundwater, it doesn't have to represent the groundwater. You can put the fixed head anywhere at any depth that you basically you believe that the situation at that depth will not affect our infiltration rate. So 4 meters is probably more than enough. So this is a fixed head boundary. So I'm going to just add this fixed head boundary. It's going to automatically place it up there. So what I'm going to do is that I'll just drag it down here. Let me zoom out a little bit so that we can see the whole model. And then all I need to do is to fix the head. So I say the head for this fixed head boundary is going to be the head of my groundwater, the basic elevation of my groundwater table, which is 153 meters. So I'm going to say 153 meters. And then okay, so the next thing is what I want to do is, so basically the fixed head is taken care of. All I need to do is to connect my soil layer to the fixed head boundary. So and basically there's this connector, it's called soil to fixed head connector. So I'm gonna use this one, I'm gonna pick this one, and then I'm gonna basically connect my native soil layer to my fixed head boundary. Now keep in mind that actually I'm going to run the model right now. So this is going to be just a simple infiltration. This will work as a sort of a rain garden without any under drain. Of course, we don't have an overflow yet too. We're going to add them later on. But if I run the model now, at least some part of my flow will basically infiltrate and then will recharge the groundwater. So I'll see something a little more interesting. So let's, I think it's the model is ready. I can run it right now and then I'll see some results even though the model is not complete. So let's give it a few seconds. Okay, simulation is done. Now we can look at some of the results. So for example, let's look at the flow, the infiltration flow between this soil block 1 column 2 and 1 column 3. So basically I can look at some of the some variables and so on, but I'm going to look at flow. So this is going to be my flow rate, which as you see it actually increases and then it stays at a sort of a relatively almost constant rate. I can look at my infiltration rate from the pond. So initially it's high because my soil is dry, but then the soil gets saturated and basically the infiltration rate drops to a constant level even though it's not zero, right? So we anyways, and we can look at the hydraulic head or water depth in our pond. So this is the hydraulic head in the pond. As you can see, it increases but it also decreases. So as the hydraulic head in the pond goes up, or the water depth goes up, we'll have some infiltration, and that water will actually go to the groundwater. Okay, so now what we want to do is that we want to add our basically outlet system. So we're gonna add our under drain system from the aggregate storage, our overflow, the catch basin that all this water goes into, and then eventually connect everything to our sewer network. So first what I'm going to do is that I'll add this catch basin. So the catch basin component is in a plugin called sewer system. So I'm going to add the sewer system plugin to my system, to my basically model. And what it will give me, if it give me a few things, it'll give me a sewer pipe and so on. But it also gives me this catch basin, which I'm going to use. So I'm going to add a catch basin. So this is my catch basin. This is supposed to be this block right here. So I let's assign a bottom elevation to this. So what I have is basically I haven't mentioned this here, but what I know is let's say the bottom elevation of our catch basin is 157 meters. It's the same as the bottom elevation of our aggregate layer. It really doesn't matter. What matters is the elevation of the starting and end points of the pipes. So basically let's see what kind of properties we're going to need for the catch basin. So we need the base area. I'm going to say base area is 1 square meter. The bottom elevation, I'm going to make it 157 meters. And that's pretty much it. That's all we need for this catch basin. Then then next thing what I will do is that I will add the under drain pipe. So let's first add the under drain pipe. So what I'm gonna do is I will use this connector called sewer pipe, right? So I'm gonna use the connector called sewer pipe. This is the pipe that basically it's not always under pressurized flow. It can go under, it can become basically the flow can become pressurized, but most of the time it's not. So basically I'm going to use this one, and I'm going to connect my aggregate layer to, I guess I need to aggregate layer to the catch basin. Okay, so now let's add the properties of this pipe. So basically what we have is that we have a start elevation. So that's when basically the hydraulic head in the source block, which in this case is the aggregate storage layer, should reach to this start elevation in order for flow to occur, right, in the pipe. So based on my diagram, the elevation is 157.2. So let's do that. So basically this elevation is going to be 157.2 meters. The Manning roughness coefficient is given here is 0.01. So I'm going to go with a Manning roughness coefficient of 0.01. The end elevation, now we have this riser, as I mentioned, and the end elevation is 157.9. Okay, so the riser height is basically 70 centimeters. So 157.9. So this is going to be 157.9 as the end elevation. The diameter of the pipe is 15 centimeters. So I'm going to enter 0.15. I'm not going to change the name, and then the pipe length is given to be 20 meters. So right here, 20 meters. So we need to provide the pipe length too. So we have 20 meters. Let me save my model just in case. And then now next, let's add the overflow. So the overflow, what we're going to do is that we're going to use this V-notch wear. We should actually wear with a kind of a power law equation that controls the relationship between the head above the wear and the flow rate. So and in this case, what we know is basically any water that goes beyond this overflow will overflow almost immediately into our catch basin. So we want to use some parameters that, you know, the coefficient, we're going to assign some large enough coefficients so that it allows water to just immediately go to the catch basin. So this the wear is actually a connector. So what I'm going to do is that I'll connect my pond to the catch basin. Now let's assign some of the properties of this wear. So the crest elevation is our actually wear elevation. So here we say the elevation of the wear is 158.2. So it's basically 20 centimeters above the bottom elevation of the pond. So what we're allowing 20 centimeters of water accumulation in the pond before the overflow to happen. So let's assign that one. So basically this is going to be 158.2. The exponent beta, I'm going to keep it at 2.5, which is for a V-notch wear. And the coefficient, I'm going to make it large enough so that I'm going to assign this value of 1000 to allow flow to be almost immediate. So basically we have no accumulation beyond the wear in our pond. Okay, so that's what we have right now. Now one last thing we need to do is, okay, so the last step is to add our essentially sewer pipe here, which is our basically it's a boundary condition essentially. What I'm going to do is that I will model the sewer pipe as a fixed head boundary, because the assumption is that the hydraulic head in the sewer pipe is not going to be affected by our bioretention system. If you want to model the system as part of a bigger sewer network, then you have to actually add basically connect this to an actual sewer network. But our purpose here is only to model the performance of a bioretention system, so we don't need to do that. So I'm going to use and by the way, I'm going to assume that the elevation of the sewer pipe is at 155 meters. So what I'm going to do is basically I'm going to use another fixed head boundary, and all I need to do is to basically assign a head of 155 to this fixed head boundary. So it's going to be 155. Now now what we need to do is that we need to connect our catch basin to the fixed head boundary so that we allow the effluent to leave the system. So what I'm going to do, I'm going to use this sewer pipe link. The properties that I'm going to assign to my sewer pipe is the same as, pretty much the same as this under drain pipe. So the diameter is 15 centimeters, the manning is 0.01, but the length I'm gonna assume is 10 meters. So oh, by the way, I need the start and end elevation too. So let's do the start elevation. So if you look, the start elevation of it's not specified here, but let's say the start elevation of our pipe is the same as, or maybe 10 centimeters above the bottom of our catch basin. So the bottom of the catch basin is 157. So I'm going to say this is 157.1. 157.1. The manning roughness is going to be 0.01. The end elevation is, I'm going to say it's the same as the head in my sewer. So I'm going to say 155. The diameter is 0.15, and the pipe length is 10. Okay, so I guess everything should be ready now. Our model is complete as far as I know. So let's just run the model and see what the results are. So I'm going to now run the model. Okay, now the simulation is finished. Let's check some results. So I'm going to first, let's look at the water level in our pond. So I can look at the water depth in our pond throughout the simulation. As you can see, it's, most of the time it stays pretty low, except for this big rain event where it actually exceeds the 0.2. And then at that time, we should have some overflow happening. So let's check the overflow rate. So I'm going to right click on this where link, and then I can look at the flow rate. And as you can see, some overflow happens. The rate is not very significant, but some overflow happens. Then we can look at our under drain rate. So this is the under drain rate. So this is the flow rate that leaves the system through the under drain. We can look at the hydraulic head in our aggregate layer, let's say. Or actually, yeah, we can look at water depth or the hydraulic head. Let's look at the hydraulic head. So this is the hydraulic head. As you can see, most of the time the hydraulic head does not reach to it's actually, yes, it exceeds our elevation of the under drain pipe. So that's where the flow happens through the under drain pipe. If I want to look at the overall flow out of our system, I can use this link. So this is the overall flow out of our system throughout the simulation. And other thing, I can look at the total infiltration rate that happened. So this is the infiltration rate throughout the simulation, and that's pretty much it. So we can actually use the same model to do some water quality modeling, and I'll do that in the future. I use the same model, I'll add some pollutants, and I'll show you how to model transport and transformation of nutrients, pollutants, and so forth in the bioretention system. Thank you for watching.